Okay, the last thing that we need to talk about for this lesson is the passive sign convention. And it might seem like the passive sign convention at first is not a very critical part of circuit analysis, but I hope that you'll see by the time we finish this discussion, as well as the two examples that follow, that the passive sign convention is really part of every single calculation that we're going to be performing. So the thing to know is that there are two types of circuit elements. There are active elements and then there are passive elements. Active elements are elements that are going to add energy to the circuit. So voltage sources and current sources are really the two most common examples of that. But passive devices, on the other hand, can only receive energy from the circuit. And so a passive device, a resistor, is the best example of a passive device. You know, you could think another example of this would be a light bulb. A light bulb, especially old-timey incandescent bulbs, are really just resistors in a glass container. So if you had a light bulb, you wouldn't really have any energy. It can only absorb or receive energy from whatever the power supply is. So a good thing to think about is an example of a roller coaster. I'm gonna flash forward here to the figures. If you look at the left side of figure 8, that's that click 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 click. Oh, I've made a horrible mistake. Part of the roller coaster where it's adding energy to the cars and to the people in the roller coaster. Once you reach the top, of course, then that becomes the picture here on the right, where you're now going to go down. You're gonna be delivering energy back. You're going to be giving energy back that has been delivered to you. In the same way, this roller coaster part on the left is like an active device that's adding energy to the circuit, whereas the falls and things like that, that's going to be the portion of the roller coaster that comes later. That's going to be the portion that is going to be like a passive device, where it's just simply absorbing energy. So if you think about it, if you're in a passive device, you always have to start at a higher elevation, and you always have to go toward a lower elevation. And the same thing is true in a circuit as well. If the circuit is going to run, passive elements must go from a higher voltage to a lower voltage. You have to be dropping voltage because, of course, we know that voltage is proportional to energy. So a passive device is going to be absorbing energy. Therefore, the electrons are going to go from a point of higher energy to a point of lower energy as they go through a passive device. Now, a shortcut for this rule is that the arrow representing the current through the resistor, or really through any passive device, will always point directly at the terminal with the plus sign for the voltage across the resistor. So if we look at figure 7, if I flash back to figure 7, which we talked about in the previous lesson, notice here that this has a current, and the arrow on the current, the arrowhead on that current, is flowing directly into the positive terminal. And that is required when you're talking about a passive device. If the arrowhead were flowing into the negative terminal, then this resistor would be violating the passive sign convention. And I know it seems like there should be more to it than that, but there really isn't. It turns out that if the arrowhead is flowing into the positive terminal, then you have the correct configuration. Now, if you find that you're analyzing a circuit and the voltage and current as they're labeled don't obey the passive sign convention, don't freak out. It's no problem. It just means that whoever drew the circuit either got the current direction wrong or they got the voltage polarity wrong, but not both, because those would cancel each other out. Now, this happens a lot when we analyze circuits, and it's something that you're going to need to become comfortable with, because when we're analyzing circuits, we're going to guess as to the direction of a current. We're going to guess as the polarity of a voltage. If we happen to get that guess wrong, it just means that we need to add a negative sign to whatever the number is. Yes, we could, of course, relabel that and put the correct current direction or put the correct voltage, but oftentimes that's been done for us, and we're asked to report back, what is V sub 1? Well, V sub 1 as it's labeled in the circuit diagram is wrong. It's backwards. How do we represent that it's backwards? With a negative sign. So we'll just put a negative sign on that quantity if we discover that it would otherwise violate the passive sign convention. So now that we've done 3 sections since your last example, you're ready to do 2 self-check examples. You have the passive sign convention example and then the Ohm's law and power sources example, both of which you should be fully prepared to do at this time.